Good afternoon. My name is Taehwan Kim from KAIST. I sincerely appreciate an opportunity to share our study. I'll be presenting our paper titled EOD, Enabling Low Latency GNN Inference via Near-Memory Concatenate Aggregation. This is the outline. I'll proceed in the following order: background, proposed method, evaluation results, and summary. Let me begin with the background of this work. Graph neural networks are becoming a popular solution in various fields. In like these applications, low latency real-time feedback is necessary to ensure user experience. Inductive learning is used to generate the predictive model, which can be generalized to newly added target nodes. This is the workflow of GNN solving system. First, in the preparation step, the requests come in, and an input graph is formed with existing node set. Second, data transfer step, prepared graphs and embeddings are transferred to AI accelerator. Finally, computation step, GNN operations such as aggregation and update are performed on the accelerator. GNN typically performs layers of aggregation and update, and it can be formulated in matrix form involving convolution matrix, feature matrix, and weight matrix. However, GNN suffers from neighborhood explosion problem, which the size of input graph grows exponentially with the number of layers. As shown in this graph, the required number of input nodes increases very rapidly as the number of layers increases. This leads to computation complexity of OBD to the power of 12, where B is the batch size, D is degree, and L is the layer depth. Now that we've discussed the background, let me move on to the proposed method. The convolution matrix can be partitioned into the 4 distinct regions. Specifically, these are first train to train, target to target, train to target, and target to train. This structure can be formulated in like this matrix form, and target to train edges are pruned. Because this setting is based on the inductive learning, where the primary goal is to compute the results for the target nodes. Then, the feature representations of each train and target node can be expressed using these equations. Based on the previous slide, pre-computation of existing train nodes is enabled before the inference, as shown here. During inference, we use these pre-computed features instead of recomputing them in real time. For train-to-target aggregation, the layer-wise dependency is decoupled, allowing computations to be performed for all layers in parallel. As a result, the computational complexity is reduced from OBD to the power of L to OBDL. However, the feature capacity overhead in memory over time becomes challenging for real-world graphs. Many previous works have utilized zero-value compression to compress the sparsity induced from value, so we adopt GVC. We proposed multi-layer concatenated zero-value compression. If we simply apply GVC to the hidden features from each layer separately, we need to add zero padding to match their length for memory access efficiency. We observed that concatenating the features from all layers helps us mitigate the imbalance in the number of zeros across different nodes. Decoupling the layer-wide dependency allows us to perform trying-to-target aggregation simultaneously across multiple layers, which in turn enables multi-layer concatenation. However, performing trying-to-target aggregation on the GPU incurs significant man copy and memory capacity pressure due to pre-computation. To address this, we offered the computation to the near-memory processing module. Aggregation process causes very irregular and sparse memory access. DIMM-based NMP architecture expands internal bandwidth and offers cost-effective memory capacity expansion, making it well suited for GNN. In addition, embeddings are gathered and reduced locally within each DIMM, it effectively lowering memcopy overhead. The hardware architecture is similar to prior NMP architectures designed for deep learning recommendation models like RegNMP. This figure shows the architecture to send the instruction. For each one instruction, we use the rank level parallelism. It starts from central support unit and rank aggregation unit to decode comment and perform aggregation. This architecture is designed for the decompression and aggregation of multi-layer concatenated node features. The NMP units shown here are dedicated specifically to train-to-target aggregation. The process begins with GVC decompression, then aggregation is performed, and finally the aggregated data from each rank is reduced in CSU. For more details, please refer to our paper. Now, the only remaining part is target-to-target part. The reduced and concatenated output from train-to-target aggregation computed by the NMP is combined here with the target features to complete the aggregation process. This target-to-target is processed on the GPU. Target-to-target requires much less GPU memory capacity and man copy compared with train-to-target. Next, I'll present the evaluation results. This is the evaluation setup. Benchmark data sets are archive papers, products, Reddit, and Yelp. Methodology is graph stage model 2 to 4 GNN layers. Hidden feature dimension 128, floating point 32. The memory system is 4 channels by 4 DIMMs by 2 ranks memory system. We modified dimension 3 for NMP simulation. Baseline is GPU and GPU pre. GPU pre means that GPU applied pre-computation, assuming GPU has enough memory capacity for pre-computation. Proposed work is about pre-computation and multi-layer concatenated GVC. Our proposed work achieves overall latency reduction compared to the baseline. It's primarily due to pre-computation and data reduction enabled by the NMP. Compared to GPU, proposed work shows lower megapin latency. It's also due to the data reduction by NMP. This figure shows accuracy validation. Pre-computation limits dynamically extending node set with newly added nodes. As new batches are added, the accuracy of the pre-computation case appears relatively lower. Therefore, periodic pre-computation refresh is required to recover the accuracy for newly added nodes. Real-world graphs have much larger node set, making the impact of newly added nodes relatively less. It means real-world graph has longer refresh period. Let me now summarize the key takeaways of this work. This work proposes pre-computation to mitigate neighborhood explosion during inference. And this work proposes multi-layer concatenated zero-value compression to improve the compression ratio and enable efficient aggregation. A DIM-based NMP module is employed to efficiently leverage pre-computation and multi-layer concatenation while expanding bandwidth and capacity. Proposed work significantly improves performance during inference as the number of layers increase compared with the baseline. Thanks for your attention. If you have any questions after the conference, please feel free to reach out to me via email.